Hello everyone, I'm Stephen Bashong, Assistant Editor at Solar Power World, and I'd like to welcome you to today's webinar, Increasing ROI with Commercial Scale Inverters. I'd also like to take a moment to thank Advanced Energy for sponsoring this webinar. Before we begin, I have just a few items to note. This webinar will be recorded. It will be available after the presentation on solarpowerworldonline.com and also will be emailed to all registrants. So this time, I'd like to introduce our presenters. Today we have Scott Kolick, who's a Senior Product Manager for Advanced Energy, and John Fiorelli, Applications Engineer at Selectria Renewables. We are thrilled to have both of you with us today. Scott will be our first presenter. Scott Kolick joined Advanced Energy, Solar Energy in March 2013 as the Senior Product Manager of the transformer-based inverter product line. Scott is responsible for transformer lifecycle product management and will be focused on supporting AE's international growth initiatives. Scott brings more than 20 years of leadership experience in the power generation and distribution industries, specifically in product management, commercial operations, sales, and engineering of electrical equipment and control systems. Scott is recognized as an industry expert in the areas of generator controls, paralleling switchgear, transfer switches, PLC, SCADA, data acquisition, and on-site power generation and distribution. Scott holds a Bachelor of Science in Electrical Engineering from the University of Minnesota. So Scott, we're happy to have you with us, and please go ahead whenever you're ready.
Okay, thank you everybody for attending this webinar. Again, my name is Scott Kolick here at Advanced Energy, and to keep on schedule, I think we're going to go through the material at a pretty fast pace, get through in 15-20 minutes in order to make sure we have some time for questions at the end. And I encourage you to download the presentation and review it at your leisure. As far as the agenda goes, I think we're going to do a very, very quick flyby of Advanced Energy just to give you an idea of who we are. But then I think we're going to lay out a base case of a typical large-scale commercial PV installation. On top of that base case, we're going to look at kind of three groups of ideas that can be used to improve the ROI of these installations. Some traditional methods, some new ideas, and some emerging ones. In the traditional bucket, we'll look at some common, but in many cases still very fruitful ways of moving the ROI needle in the right direction by reducing costs and increasing energy output. In the new bucket, we'll look at a couple of ways that are relatively new to the U.S. commercial scene, maybe going back a couple of years, and the adoption of these is going to be a little more mixed, with some developers aggressively implementing these, others on the fence, and some kind of choosing to stay on the sidelines for the moment. And then finally, in the emerging bucket, we'll take an example of what a large commercial facility might look like in, say, 3 to 5 years. And this example, I think, is going to include some technologies that many today might characterize as maybe not ready for prime time, but in our opinion, show some real promise as game-changing technologies to improve ROI. At AE, we'll do a quick flyby. At AE, we are the #3 market share leader in the world in inverters and #1 and 2 in nearly every U.S. segment. We're publicly traded. We have superb bankability and nearly 30 years of experience in power conversion solutions, and I'll kind of leave the rest to your review. The map, go backwards. The map, as you can see, we're a global company with manufacturing in U.S., Canada, India, and China. And our sales are primarily focused in U.S. and Europe, but that's changing as we put on develop some global products. And finally, from a product offering perspective, we have a full range of products all the way from small 12-kilowatt string inverters up to 500-kilowatt central inverters up to 2-megawatt integrated solutions for utilities. And we'll leave the rest for your review. Then onward into what we would say is a base case traditional system. We'll use some characteristics of this system that I think are pretty common. We'll have 600-volt stringing with, say, 12 to 15 panels per string. We'll have combiner boxes near the array, typically aggregating maybe 20 or so strings. The combiner boxes will come back to pad-mounted central inverters, maybe 100, 250, or 500 kilowatt rated. We'll have DC-AC ratios in the 1.1, maybe to 1.25 to 1 ratio, with the DC-AC being the power output of the panels versus the inverter nameplate rating. And for larger installations, inverters would typically have maybe sub-combiners of fuses or breakers. We put some kind of monitoring in there, either at the inverter level or revenue grade monitoring, for example, and we may even monitor the sub-combiner inputs. There's a lot of installations that I would say may not fit this exact model, but I think this is a good typical characterization that we can build on for this presentation. As far as some traditional ROI improvement methods, there are quite a few out there, and I think there's still plenty of room in a lot of these areas to cut capital costs and increase energy harvest. The racking and structural systems, for example, of commercial rooftops, a great example. If you look at GTM data, for example, on say a $3 per watt commercial rooftop installation, these two subsystems can cost on the order of 35 cents a watt, which is almost 10% of the total. So pre-assembled components, assemblies that allow you to do assembly line procedures on site, those are all methods that can be used to improve the ROI. On the electrical balance of system side, those systems can be typically 50 cents a watt on the order. So, systems that reduce conduit runs and wiring, such as reducing neutral DC home runs and being able to take native transformerless inverters and connect them together to, into one transformer. Those are all good ways, I think, of reducing electrical costs. On the energy harvest side, panel efficiency will, of course, continue to get attention with, I'll say, a rule of thumb of 1% efficiency gain in the panels is on the order of 4 to 5 cents per watt savings. So I think we'll continue, of course, to see efficiency improvements there. A clear winner is a choice, choosing inverters with high uptime reliability and lifetime equal to that of the panels is also critically important. A rule of thumb is, 3.5 days of downtime, for example, is equal to a full 1% efficiency loss. So, getting that, inverter efficiency is of course important, but the uptime and availability of that inverter is a very, very important thing to consider in the ROI equation. Finally, trackers, as we know, are good for some applications, and MPPT algorithms that have wider ranges, for example, MPT ranges that have lower turn-on voltages, and installations that are, I'll say, less than optimal from the array perspective, these types of features can really help on the energy harvest side. And finally, I'd say that, the use of good modeling tools in the hands of a very skilled application engineer, it can go a long ways to getting the most out of your PV system. So those I just kind of bring as background of the things that have kind of typically been on the landscape for a while. Now, when we switch to new methods, without a doubt, I think one of the hottest topics out there right now is the use of three-phase string and distributed inverters in commercial applications. Now, solutions, as you know, are very common in Europe, and they are certainly gaining traction here in the U.S. There are some clear advantages to this solution in the commercial space. I'll say first and foremost is just the ability to get a better match between the array output power and the inverter rating, just by virtue of using smaller building blocks, say in the 15 to 25, maybe up to 40 kilowatt range. You're only paying for the amount of inverter that you need. You cut DC combiner boxes, they are eliminated, and you can reduce DC wiring. As we bring the smaller inverters up into the array onto the roof, we can cut the DC balancer system by quite a bit. Now, there is a need for AC collection, of course, but really AC panel boards are much more of a commodity, much lower cost, I'll say, than their DC counterparts. So shifting the cost from DC to AC is a big help on the ROI. Other benefits of reduced mounting space and simpler install for things like, rigging equipment. You don't need the heavy rigging of those small string inverters is another good example. And finally, I'll say because of the small size and simple install, the ability to unhook an inverter and quickly plug in a replacement, that feature alone can cut some downtime and increase availability, which of course translates to increased energy harvest. So, as far as the numbers, we've seen some claims out there of up to 10 cents a watt for each of the AC and DC balancer system and labor buckets, and energy harvest gains up to 2%. I think we would advise, some caution in applying these to individual projects. as the assumptions underneath some of those models just certainly can't apply to all of the different projects. So I think it really needs to be looked at on a project by project basis. And to be fair, I think there are some potential downsides and things to watch out for in this and decentralized and string inverters. I mean, first and foremost is just the sheer quantity of inverters it takes to build up a large scale commercial application. So, and the likelihood of an inverter service event is going to increase linearly with the amount of inverters. You're also going to have a much more complex wiring on the roof, both AC and DC. Bringing all of that AC wiring back to large collector switchboards can be complicated. And just the whole issue of being able to access equipment on the roof, that may or may not be easy in all applications. So despite these downsides, I think the majority of analysts and thinkers in this space are projecting, I would say, a very robust adoption of three-phase string in the commercial applications. And again, they're not a perfect fit for all applications, but certainly we see this trend increasing. Next, we'll talk about DC to AC ratios. DC to AC ratios, and specifically the use of higher DC to AC ratios to improve ROI. I think we've all seen pretty dramatic price declines in PV panels, and according to GTM, this is going to continue. I think we'll see panels, down in the 40 cent a watt range by 2016. So that certainly helps ROI. But when PV panel prices were higher, I think right sizing in the inverter really meant matching the peak power of the array to the inverter power, with the idea that would eliminate some wasteful power clipping. And this kind of resulted in DC-AC ratios in the, I'll say 1.15 or 1.25 to 1 ratio, just enough to account for losses, temperature, soiling, panel degradation, those types of things. And the idea behind DC-AC ratios or higher DC-AC ratios is that you get greater energy harvest during lower radiance levels, just by virtue of the greater number of panels. And that benefit of that extra energy harvest offsets the additional cost of the PV panels and produces an overall better ROI. And really it's the declining price of the PV panels which has kind of enabled this equation to work. Now at higher DC-AC ratios, the inverter is going to operate at full power for longer periods of time during the day, and it will be power limited with MPPT turned off during peak periods of time, kind of making the whole issue of inverter peak efficiency far less relevant. And even farther than that, if you look at the CEC efficiency inverters that would be running at high DC to AC ratio, this is also, I would say, very significantly reduced because, as you know, the CEC is a weighted efficiency with, I think, about 95% of that weighting corresponding to loading that's 75% or less. So as that inverter operates more of its life at the 100% load, really the CEC efficiency becomes much less of an issue. And the bottom line is that, with high DC-AC ratios can make sense for a lot of commercial applications by increasing energy production and operating income and increasing ROI. The next method, I say, second only to the string versus central inverter discussion, is really the use of 1,000 volt DC in commercial applications. As far as ROI improvements, the premise of the 1,000 volt versus 600 volt is really a reduction of the electrical balance of system costs and increased efficiency due to less wiring. We'll touch on this in a little bit more in a minute. As I'm sure you're aware, higher voltages are common in Europe. In fact, up to 1,500 volt is becoming typical in Europe. And large ground mount utility systems here in the U.S. have been at 1,000 volt for quite some time. And there's really, I think, been two barriers that we have seen that have slowed this adoption in the U.S. One is the availability of you all listed 1,000 volt equipment, and the second is really the permitting and the approval of the authorities having jurisdiction. Now, unlike utility systems that are designed around the NESC, which is a National Electrical Safety Code, public and private premises wiring needs to comply with the NEC and typically requires the use of all UL listed equipment. And in the past, there just simply wasn't enough demand in the market for that equipment for commercial applications to entice suppliers to go through the redesigns and the listing. And that that certainly is changing. Now, the issue of permitting and approval by the authority having jurisdiction is a little more of a complicated and difficult issue. For example, the NEC sections such as 690.8 that, that address PV systems greater than 600 volts, they ask for generic compliance with, quote, other requirements applicable to installations over 600 volts. Now, statements like that in the code really leave a lot open to the interpretation of the authorities having jurisdiction. And then when you add to the fact that a lot of the AHJs typically just don't spend a lot of time on systems above 480 volt, you can begin to kind of get a feel for the difficulties and the risk associated with permitting on the 600 volt and up greater than 600 volt systems. So, and these additional risks can drive some incremental permitting costs and project delays that I can say can easily negate the benefits of 1,000 volts. So there is hope, I would say, in the 2014 code that some of that ambiguity will be cleared up and some of these other roadblocks will be cleared. As far as the ROI-enhancing benefits of the 1,000 volt really stem from the fact that as the voltage goes up, the current comes down. That cuts the wire size, it cuts the amount and the cost of the DC system that's to be put in place. Now, we're also seeing the amount of PV panels per string increase, so all of that translates to much lower costs on the DC side. Now, I'm hesitant to use a broad brushstroke and throw out a number for the savings on the 1,000 volt, but if you go back to GTM, they're saying that there is probably a range of 3 cents to 7 cents a watt for the move from 600 to 1,000 volt, and to us, I think that seems reasonable. So, to be balanced, I think there are some downsides to the 1,000 volt as well that I think you need to be careful from. I think we've covered some of that on the permitting side, but also I would add on the safety and the training side. Higher voltages clearly come with some additional risks. So a lot of us probably have children who have survived putting something in a wall outlet at 120 volt that shouldn't be there. And the reality is lower voltages are much more forgiving. So as the voltages increase, safety issues are going to come into play. So, and arc flash and arc potential as the voltage goes up is clearly another area that needs to be taken care of. So I would say that greater care and attention to the workmanship and the installation of 1,000 volt versus 600 volt systems is clearly, I'll say, warranted. But I'll say just like the trend upwards of distributed string and commercial, we expect this trend to continue to the point, I think, where 1,000 volt, we believe, will be the norm for large commercial applications. Okay, farther out, I think you will see, if we can just take the last few minutes to kind of dream a little bit, farther out, I think you're going to see large commercial facilities take a lot more control and ownership over their energy consumption and costs. And a key driver of this, we believe, will be the emergence of affordable energy storage that will turn the PV system into a controllable, dispatchable asset. If you look at the slide that I'm showing here, I'm showing a PV system and a battery system both sitting on one DC bus to a common inverter into the facility grid. And also on that facility grid, like many large commercial facilities, we have standby generators, maybe gas, maybe diesel. There are loads that are controlled by building automation systems and other intelligent systems. And you have some point of common coupling or connection to the utility grid. Okay. And I think what you're going to see is the emergence of some enterprise level control, I'll say, or higher level intelligence that is going to be able to control all of these elements in a large commercial facility to optimize and lower energy costs. So the enterprise level control will look at the utility side and look at the price of electricity, look at the demand for electricity on that facility, and we can charge batteries, discharge batteries, start generators, stop generators, increase and decrease loads in the optimal way to get the lowest possible energy cost for that facility. And if you look beyond that, markets like PJM and are opening up more and more for large commercial facilities to actually participate in the energy market. So as prices of electricity go up in the market, facilities with on-site power generation can actually sell power back if they have an excess and use that for ROI. So all of these things are that we see are developing. The technologies are, some of them are there today, some of them aren't quite ready, or their costs are just prohibitive. But I think this is we believe, an interesting view of what a large commercial facility may look like. With that, I think we'll turn it over to the next presenter, so we have some time at the end for questions.
Thanks so much for that great presentation, Scott. Now we'll be hearing from John Fiorelli. He's the applications engineer at Selectria Renewables. Here's a little bit about John. John has worked in the PV industry for over 5 years. He has been involved in all phases of commercial PV design, installation, commissioning, and O&M. Prior to joining Selectria Renewables, John was an applications engineer for SatCon Technology. His experience in training as an NAB CEP certified PV installer has helped to excel in the field of solar. John joined the Selectria team in March 2013. So thanks again for being with us here today, John. Please take it away.
Stephen, thanks a lot, and thanks to Scott for setting up a good groundwork presentation there. A lot of great things happening today, and a lot of great things on the horizon. So we can all be excited about where our industry, our shared industry, is headed. As Stephen mentioned, my background is a designer, installer, and applications engineer at another inverter company once based in Massachusetts. So I bring to the table some perspective on design considerations. I bring to the table perspective on means to look at a design and look at it in ways to increase the ROI, at the system level and the inverter level. At SatCon, as part of optimizing projects that were hundreds of megawatts in size from all over the world. So got some shared experience, and I think you'll see that here in the slides that I'll be presenting. A little bit about Selectria is that based in Lawrence, Massachusetts, we basically got our start in the electric vehicle industry back in the 80s, and we took the technology that we developed and we applied it to the PV inverter sort of industry. We've got commercial three-phase inverters from 10 kW up to 500 kW. So, when we talk about commercial inverters, those are the products that Selectria has in that space. So, I'm going to be talking about design considerations. I'm going to be talking about inverter integrated options. I'll also be talking about post-inverter installation considerations. And all of these things, of course, relate to the theme of this webinar, that these are things that impact the system, the inverter's ROI. And I'll start by talking about the design considerations. And, Scott had mentioned 1,000-volt systems, and it's very exciting development on the horizon. And I think, and it's actually here today. But actually, let me take a step back and talk about just generally on design considerations. In any system, there's going to be dozens of design decisions, and there's going to be value to those decisions, and there's going to be costs associated with those decisions. So, how do you capture those, the impacts, the influences of all those different levers, all those different knobs when it comes to a system design? And really, it's all captured in the financial model of the system. And, so from my experience, a good sort of recommendation from a designer standpoint, from a developer standpoint, is to be able to develop a model that quickly quantifies the effects, higher string size or a higher AC to DC ratio, just because there are so many different levers that it's important to be able to quickly, rapidly quantify, the impacts of such decisions. I can speak from experience that a lot of times you don't have a lot of time to crank out proposals, to respond to RFPs. So it's important that that model it is quick, easy to use. And one thing to mention is that from a design standpoint, it's true that there really are very few rules of thumb because of the fact that the goals among different projects vary significantly. The challenge that you face with different sites and the different design considerations for those projects vary. So, as well as the financial models vary. It's a sort of PV 101 when it comes to system design. And as Scott had mentioned, with the benefits of 1,000-volt systems, there's benefit to designing a system to the maximum number of modules per string. And what that gives you, or the benefit that that gives you, is that it gives you reduced BOS costs, because you basically have fewer strings for the same power. So fewer strings means fewer combiner boxes, means fewer source circuits and home run circuits. It also gives you the benefit of reduced losses. You've got less conductors that are dissipating heat and wasting energy. It also adds the value to ensure that the voltage of your system, it stays within the MPPT tracking range of the system for its life. Now, when you do your string sizing, you'll get a range many times you'll get a range of allowable strings. And that's not to say that every time you need to use that maximum number of modules per string. There's always going to be unique situations. There's always going to be other design considerations that are all kind of forming this final design, or forming this design to its final form. Sometimes the maximum string size is an odd number. It doesn't work well with your racking or your carport. So, back to that point that there's no rules of thumb. Sure, you want to try to maximize your number of modules per string, but you can't always do that. And taking this to the next step, right now most commercial systems is 600 volts. But think of the added benefits to 1,000-volt systems that are on the horizon. There's a lot of tricks of the trade when it comes to optimizing your system to maximize your ROI. And one of those such, I'm calling it a trick of the trade, but I don't want to be so crass, is to use a more accurate source of temperature information. And starting with the 2011 NEC, there has been there's a note in the code that basically talks about how that one sort of acceptable source of accurate temperatures is the so-called ash rate temperatures. And the low ash rate temperature, which basically controls your low design temperature, which controls your maximum number of modules per string, there's benefit to using a higher temperature than what's been traditionally used in the industry, which has been the record low temperature. The ash rate temperature is basically, it's a little bit higher, and it reflects a more accurate temperature that that you can expect when the panels, when the strings are exposed to sunlight. And basically, by using that high temperature, in many cases, it allows you to design to an additional panel per string, which, as you've heard time and time again in this webinar, that there's benefits to, there's cost savings benefits, there's performance benefits to being able to select a larger or a larger string size. But one disclaimer there is that you always want to check with your inspector. There are still a lot of areas that are on the 2008 NEC. Doesn't mean that that you can't use the ash rate temperatures, but you should check with your inspector to make sure that they are comfortable with you using those temperatures. And as the last slide showed, there's an online tool from Solar ABC that allows you to quickly determine those temperatures. Now, here's an example. Here's an example of a system that the strings were sized with the sort of traditional temperatures, the record low and the average high, and then a system that was the strings were sized with the ASHRAE temperatures. And this is a 500 kW system. It's arbitrarily chosen for Atlantic City, New Jersey, and you can see that through using those temperature, the ASHRAE temperature specifically, you can design the system with one less combiner box, and that's real savings. In fact, you could take that, being in Atlantic City, you could take that savings and maybe head to the tables and increase your ROI in other ways, or maybe decrease your ROI depending on how you look at it. All right, so moving on to the next slide here. Sorry for the delay here, guys. And I'll talk to this slide before it pops up. It's a lot of the things that have already been discussed about oversizing. Rewind a couple years, and the price of modules were say twice as what they are today, and as a result, designers and installers, they didn't want to sacrifice any production from any module in the array. That meant attempting to do optimal tilt angles, orientation. That meant not installing modules in shaded regions of roofs. And now with the lower module costs, lower module prices, you can now explore flexibility by using higher DC to AC ratios. And the sort of the math in the background to it is that you're always going to get more production with a larger array feeding a fixed size inverter. And so you're basically, the incremental cost of adding those panels has decreased. So basically you can run analysis where you vary the DC side with this fixed size inverter, and you can look at the effects of array to inverter ratio on your annual production. So that gives you flexibility from a design standpoint. And I'm just making one note here because my slides are for some reason they are not advancing. So just bear with me for 1 second as we make through this little technical difficulty. So, I'll continue to talk about the AC to DC ratios. A key, I think another huge driver to using higher DC to AC ratios, rather, is that many utilities have time of use rate structures. So basically, the highest valued energy or the highest feed-in tariff or feed-in rate or payback rate is during the summertime, and it's during those peak hours. So if you utilize a higher DC to AC ratio, then you can ensure that you're going to have the maximum production when the energy is. In the next slide, there's just basically a list of other design considerations, and we don't have time to go through all of these, and we could spend a whole webinar talking about these. But other things to consider are the location of the inverter in the array. Do you make your longest run DC, or do you make it longest run AC? Well, there's considerations such as inverter efficiency. But the key there is that all the efficiency in the world doesn't matter if your inverter doesn't run. There's considerations for module specifications. The efficiency of the modules is one key spec that can impact your system costs and impact your ROI. The degradation rate of the modules. Another key driver in determining the ROI of your system. You could also say accurately the IP rating. How well that module will withstand the elements. That's another important spec. Other design considerations. Aluminum versus copper wire. That's a great one. And lastly, the consideration for what's the best combiner box configuration? Do you go with few large combiner boxes that can contain a lot of strings, or do you go with more smaller combiner boxes? And really, there's no cut and dry answer on which one of those configurations are the best, because it all depends. It all depends on the unique considerations for your project. Maybe the roof, for example, your roof is situated in such a way that it makes sense to have just one combiner box for a given area of that roof, and those combiner boxes happen to be of larger variety. So that's just an example of case by case. You'll have to run the cost-benefit analysis, plug it into your financial model to determine what is the optimal design for your system. So with that, we'll wrap up the design considerations, and we will move on to sort of the next of the three topics covered today on my webinar, Selectria's portion of the webinar, that is, and it relates to inverter options. So, the name of the game with inverter options is basically, take the installation of options or componentry out of the field and basically do it in the factory. So you can save costs, installation labor. You can save, engineering costs, procurement costs, as far as having someone. You still have someone help work with your inverter provider to spec the components, but there's less overhead involved in managing working with different vendors. And when it comes to inverter options, there's a variety of options available. The most common is the subcombiner options, and that takes the variety of using input fuses in that subcombiner or using breakers. The breaker option basically has an added or a sort of hidden value in that, in areas subject to the 2011 NEC, you might have, or not might have, but you'll have fuse serviceability requirements. And that basically dictate that a fuse in the array will need to be isolated from both ends for safety reasons. And so if you have fuses, you've got to use external disconnects to isolate that fuse. Now, the breaker basically, because a breaker is not a device that has fuse, it's not a fuse, so it basically is not subject to those same fusibility requirements. So a lot of installers go that route to save from having to install a set of disconnect switches. Other inverter integrated options include revenue grade metering, zone level monitoring, where you're basically monitoring the input current through each fuse of your subcombiner. That's one that is tricky because it adds to your system cost, but it gives you a tremendous amount of troubleshooting capability. So it basically, where it adds on one hand to your system cost, it basically saves you money on the troubleshooting side. And then lastly, another option to discuss when we talk about inverter options is monitoring, web-based monitoring. There's value of going with the inverter company's web-based monitoring software, because things like the gateway card would be integrated in the factory, And you know, I think a huge benefit that's really not discussed very often is the benefit of going with one company for your inverter and monitoring, and the fact that it basically gives your inverter company visibility to your site. So, you know, application engineers like myself can log into that web-based monitoring site. Ours is called SolarInView. So we log into the SolarInView website and, you know, be able to talk about things that maybe the customer is seeing, and, you know, help the customer with troubleshooting issues that may be happening in the array. You know, why is the shape of the daily production curve have a chunk taken out in the morning? Well, maybe there's shading in the morning. So, you know, those are conversations that, you know, from an application standpoint, it's helpful to be able to quickly log into web-based monitoring and provide that good support. So, you know, the last, you know, section of the presentation that I'll cover today relates to the basically post installation ways to increase the ROI of your system, of your inverter. And, you know, on this slide I have a list of just different things to consider. You know, and it's back to, you know, at least weighing sort of the cost benefit. There's a cost associated with doing things, many of the things on this list, but there's a benefit to be gained as well, and it's, you know, up to you as a designer and installer to decide what your priorities are on the project. So, you know, there's I think you know, something that is something that you don't want to make a question is preventative maintenance. You know, just my experience working in the field and working with field engineers is that preventative maintenance is one of those big opportunities that customers a lot of times they neglect. And, you know, we don't want to give the impression that PV is totally without maintenance. You know, you want to have your annual or biannual maintenance checks where you check the torques of the inverters. You know, you clean you clean the input vents and filters, and you check your communication wiring. And, you know, the inverter, as though it doesn't have any moving parts, you know, any inverter is going to vibrate slightly, and there's expansion and contraction in connections that are temperature driven by temperature changes. So, you know, you want to make sure that, you know, you have a good preventative maintenance plan, and, you know, your inverter provider will be able to provide preventative maintenance guidelines for their product. So, and then, of course, if that's something you'd rather have the inverter experts cover, there's the possibility of going with a preventative maintenance plan from the inverter company. There's extended warranty options. There's uptime guarantee options. You know, I think there's, you know, several key service parts that every customer should have for their project just to ensure uptime. I think one of the sort of opportunities as well is to have a fault sort of response plan. You know, have your plan ready. You know your installer, the O&M provider, and have your inverter company ready on hand to respond to when you do have an issue. And, you know, the inverter sometimes gets a bad rap because it's the only thing that really talks and provides feedback. And just because the inverter is down doesn't mean that it's the inverter's problem. It could be a ground fault. Could be a, you know, DC voltage issue. So, all right. So, you know, that pretty much wraps up the discussion post installation considerations to increase ROI. You know, the last slide is a thank you slide, and, you know, I think that we'll hand it back over to Stephen for questions. But before I do, I think, you know, I'm proud of my trade as an application engineer, so I don't want to, so I want to, you know, use the opportunity to talk about how, you know, application engineers, our experience, our knowledge in the product, you know, we're actually, you know, keys in helping you decide what's the best project or product rather, and helping you, you know, learn from our experience of supporting, hundreds, thousands of projects every year and sharing sort of best practices. So don't discount the application engineer as a means to increase that ROI. And with that, I'll hand it back over to Steve.
Thank you so much, John, for that excellent presentation. And now, after all of that information, I'm sure the audience has some questions. So we'll begin with those. But I want to remind you that you can submit questions at any time in your GoToMeeting panel on your right. The first question I have is for Scott with Advanced Energy. Could you tell us more about three-phase inverters and when they're most beneficial?
Yeah, right now, I mean, all of our inverters are three-phase, all the way from string through central up to the large utility systems. So we're probably not in a good position. We do not operate in the residential sort of single-phase space here at AE. So.
Very good. I have another one for you. Is there a situation when the use of higher DC-AC ratios doesn't make sense?
Yeah, I would say yes, there is. I think if you have a large rooftop, I'll say sort of optimal conditions, not a lot of shading, not a lot of angles, where it's a very good roof. I mean, really, the benefits of a higher DC-AC ratio certainly start to go away. So, I think, typical commercial applications, oftentimes don't have optimal roofs. So I think that's where you want to focus on high DC-AC.
All right, thank you, Scott. This could go. Maybe John could take this one first, but then Scott. Vladimir says, my understanding was that inverters require major overhauls after 10 to 15 years. Is that still true today? Would all inverters require that type of maintenance?
No, see, the inverter, I can speak to selector inverters, and I'm sure Advanced Energy is similar, is that, they have a 20-year design life. We offer extended warranties up to that point. Where Vladimir might be thinking of the string inverter side, where there is sort of less of a shorter design life, but for a commercial inverter, that's just not the case.
Scott, did you have any input on that?
No, I would agree. I think we design them for a 20+ year lifetime, so there's preventative maintenance, there's filters, there's various other things, but we do not design them with the need for major replacements of parts inside.
Great. I have another question. At what size system does three-phase string inverters give way to three-phase central inverters in terms of increased ROI? Several hundred kW?
That's a great question, and I would say our position here is that I guess the answer is it depends. I mean, we've seen there's just so many factors that will make the string versus central kind of swing each way. So I would say I think you got to look at each project individually to kind of figure out which one makes sense. So there's a lot of people that I think will say, pick a kilowatt level and say below this is one and above this with this. And in our experience, that's just not the right way of looking at it.
Okay. John, anything?
No, that's well said.
I have a follow-up from Vladimir, who would like to know, is your standard warranty 20 to 25 years?
I can take that one. So our standard warranty for our commercial three-phase inverters is 5 years, and it can be extended up to 20 years in 5-year increments.
I have another question. It's a follow-up from Larry. Why do central inverters typically have a 5-year warranty and string inverters have a 10-year warranty if they're both made for a long-term lifespan?
Yeah, my view is that it's basically sort of the industry practice that's what the competition and what the market is sort of setting as the minimum warranty requirement. It gives the customer the choice to to extend that warranty if they'd like. But if they're comfortable with the 5-year, then that's their prerogative.
Okay, this is Scott here. We got unhooked, but we're back.
Great. Scott, I have a question here. Should we be training our workers for 1,000 watt or 1,000 volt inverters now?
Yeah, that I think is going to have to be kind of each developer is going to kind of have to wrestle with that themselves. But I would say that the 1,000 volt trend from our perspective is growing, and it is going to happen. And I just would say that the training issues around 1,000 volt, as in any high voltage system, is something that really needs to be thought through well. So, but as far as timing, I mean, I would leave that to the developers.
All right, thank you, Scott. And John, I think we have time for one last question. If you have time, we mentioned, or that you mentioned that there are a few. Excuse me. You mentioned that there are a few rules of thumb. Can you mention those?
Oh, right. So rules of thumb. I mean, on one single MPPT channel, you don't want to use 2 different string sizes. I mean, that's kind of a best design practice rather than a rule of thumb. Also voltage drop. So you want to design to try to minimize your DC voltage drop less than 1.5 to 2%, and your AC voltage drop less than 0.5 to 1%. I think that's a good rule of thumb. But at the same time, I could think of a project that I worked on where we were on a landfill, and we could only put the inverters on one side of that landfill. It was a 5 megawatt project. So you could imagine the wiring runs that were from the far end of the landfill to the inverters, and as a result, we had voltage drops of 2.5% on that one. So I guess that just kind of drives home that the point that there are a few rules of thumb, and each you would maybe call. There's a lot of sort of good design guides, but sometimes you have to have flexibility because of the unique project aspects of a project.
All right. Well, I do believe that's all we have time for today. I'd like to thank John and Scott for being here to share their expertise with us. And I'd also like to thank Advanced Energy for sponsoring the webinar. Also, thanks to everyone in our audience for listening. I hope you enjoyed our presentation. Please join us for future Solar Power World webinars. There is a lot more to come. Thanks, everybody.